j. So I know in engineering we use j, but we do it in the same way. Okay, now the next way you write complex numbers is in exponential form. So this is exponential form. Now, if you have a purely imaginary complex number, you say z is equal to let's see, bj. Okay, so here z is purely imaginary. It does not have a real part. What you can do, okay, now what you can do is you can rewrite e to the power of bj. You shouldn't use b here, I'm going to use theta. Okay, because theta is a number. Okay, so theta is measured here in radians. So theta is measured in radians, and you know radians, we usually write them to 3 decimal places, and you can get any value of radians. So e to the power of theta j, this is actually equal to cos of theta plus j sine theta. Now, if you read the introduction to this chapter, the reason this is true is because of what we call power series. Okay, there's a power series expression for e to the power of x, and then there's also a power series expression for sine x and cos x. Now, there's a question as one of your exercises to do. I didn't want to go into that because we are still going to do the Maclaurin power series later on. So for now, we don't really need it. But you can actually show that if you combine cos theta and j sine theta in the way that they are written in the Maclaurin series, you will have e to the power of theta j. Now we know that this is one way of writing a complex number in polar form. Okay, so we wrote it up here. There it is. So that is in polar form. The only thing missing is the r, and when r is not written, it means that r is equal to 1. So this means that e to the power of theta j, this is just equal to 1, and then your angle is theta. Okay, so if I have a complex number where r is not equal to 1, let's say I have z, this is equal to some r, and then theta. I can still rewrite this in exponential form because I know this part over here is equal to that one. All I do is say this is r, and then I rewrite theta j, and this is still the same thing as that one over there. Okay, so any complex number can be written in polar, so it can be written in exponential form. Okay, and look at an example over here. Converting between polar and exponential form. So examples. So let's say we have a complex number z. This is 2, and that is 30 degrees over there. Now I need to convert this to exponential form. Now, very important, in exponential form, theta must be in radians. If theta is not in radians, then what you have written is undefined, or it doesn't have a meaning. So if I put an angle there that is like in degrees, it doesn't have a meaning. You must convert your angle to radians if it is not already in radians. Now we look at our example over here. My angle 30 degrees is obviously not in radians, it's in degrees. So I need to convert it. So to do that, I know that 30 degrees, this is just equal to pi over 6 radians. So what I do is I rewrite z. Z is equal to 2. And then here I have pi over 6. And this is radians. Okay, then you remember how we did it before. We say this part, this is just equal to E, and then my angle theta pi over 6, and then I put a J, then this 2 just multiplies it like that. So if I have my complex number in polar form, like I do over here, first thing I need to do, convert my angle into radians. Then when I have it like that, this part that I have in the rectangle becomes the exponent of E with a J, and then I multiply it with whatever value of R that I have over there. Let's do some more examples. Okay, I'm trying to scroll up. Okay. I have 3 and then minus 60 degrees. Okay, so here again, I want to first convert my angle minus 60 degrees into radians, because otherwise when I rewrite it in exponential form, it doesn't have a meaning. So minus 60 degrees, this is just equal to minus pi over 3 radians. Okay, so this I can rewrite it 3 minus pi over 3, and this is in radians. Okay, then to rewrite this is just 3 e to the power of minus pi over 3, and then I put a j over there. So that is how I rewrite it in exponential form. So it's not always exponential form. So it's not just polar form to exponential form. You could have z in rectangular form, square root of 2 minus j. So we can also rewrite this one in exponential form. So to do that, I just need to know what is r and what is theta. So r, work it out in the same way. This is the square root of the square root of 2 squared plus minus 1 squared. So this is just equal to the square root of 3. Now this angle over here is in the third quadrant. Okay, because not third quadrant, it's in the fourth quadrant. It's in the fourth quadrant because x is positive and y is negative. So this is where it is. So it's in the fourth quadrant. So if I want to work out what my angle is, I can do this in one step. So I don't need to work out what it is in degrees and then convert it. I just set my calculator to radian mode. And I know that because it's in the fourth quadrant, the answer will just be 2 pi minus tan inverse of 1 over the square root of 2. Okay, so here the 1 is positive and this one is positive because this part is me working out the reference angle. Okay, so that's how we would work out the reference angle. And then after I have my reference angle, because it is in quadrant 4, I must subtract it from 2 pi. So put your calculator into radians, excuse me, and then you work it out. That is tan inverse of 1 square root of 2. Okay. Okay, I am getting 5.66. Okay, so this is 5.668 radians. Okay, now this, it kind of makes sense because 2 pi is 360 and pi is 3 point something. So this is a number very close to 6 point something. So that tells us that it is in the fourth quadrant. Okay, so now that I have my angle, I have r, I just substitute them into the exponential form. So I will have z, my r is square root of 3, then I have e to the power of 5.668 in j, and that's it. Okay, so very simple to do, not very complicated when you have to change between any of the forms. Let's see, another one in rectangular. This is -1 minus j. Okay, we have to convert this one to exponential form, so we can draw a sketch. Now this one is in the third quadrant because x is negative, y is negative, and in the third quadrant that is where they are both negative. Now because it's in the third quadrant, to find the angle I must say pi plus my reference angle. Okay, so here I'll start with r. R is equal to the square root of -1 squared. So squared plus -1 squared. Okay, and this is just equal to the square root of 2. Then to get theta, I said it is in the third quadrant over here. I will say pi plus tan inverse of 1/1. So I take the positive here. So I ignore the negative, ignore the negative. That's how we work it out for our reference angle. Okay, then again, remember this must be in radians if you're going to write it in exponential form. So if it's easier for you to find it in degrees and then convert it, that is fine. But I recommend you get used to rewriting it in writing it in radians straight away. So you can set your calculator to radians. It's not difficult to do. Okay, so here tan inverse of 1 we know is pi over 4. That's 45 degrees. So it's a special angle. So here I have pi plus pi over 4, and then this is equal to 5 pi over 4, and this is in radians. So I have r and I have theta. Now in exponential form, z will just be equal to the square root of 2, and then e 5 pi over 4 j. Okay, that is what we will have. Then okay, what if it's given in this form? Cos pi over 2 plus j sine pi over 2. Now this is in polar form. R and theta are given. There's no number or there's no coefficient there. That means R is equal to 1. And here theta is just the angle you're taking sine and cos of. So this is pi over 2. So to rewrite this one, my z will be equal to 1. I don't need to write it. So this is e to the power of pi over 2 times j. That's how we do it. Then if z is 3, and then it's 30 degrees. Again, polar form. Now my angle is in degrees. I will have to convert it. So I rewrite this as 3 cos sine, and this is minus pi over 6. Okay, then in exponential form, z will just be equal to 3 e to the power of minus pi over 6, and then I multiply this by j. Okay, then it's also possible to convert from exponential to polar or rectangular. That is not difficult to do because you know what r is and you know what theta is just by looking at it. So when I look at this one, I can tell r is 3 and my angle is whatever is multiplying j. So I will just remove the j, and whatever is left, that is my angle with the sign as well. So let's look at this one. I have z. This is 2 e to the power of minus j pi. So to work or to rewrite this in polar form, this is just equal to 2, and then my angle, all I need to do is remove this j over there. When I remove the j, I'm left with minus pi. Okay, so there it is in polar form. Now minus pi and pi are the same because they lie at the same position, so this is just pi. But pi and with other angles that are at the center of the, or at the border of the quadrants, like here 0, 90, let me use radians, pi over 2, pi, and 3 pi over 2. Now with these ones, we can always evaluate what sine and cos of those are, because it's usually 0, 1, or minus 1. So this is it in polar form, and I can also rewrite it in rectangular form. So this is 2 cos pi plus 2j sine of pi. Remember, the 2 should multiply the cos and the sine. So cos of pi, that is just equal to minus 1. So this is 2 minus 1. And then sine of pi, that is equal to 0. So I have plus 2j times 0. So this is in fact just equal to minus 2. So that is in rectangular form, and then the first one over here, this is in polar form. Then one more conversion. Let's say I have z. This is equal to 5 e to the power of 0.219 j. Now to rewrite this in excuse me, in polar and rectangular form is not difficult. This is my r, that is my theta. What I do is say this is equal to 5, and then I have 0.219. This is a 9. Okay, so there it is in polar form. And then to convert this into rectangular form, we know that this part means cos of that angle plus j sine of that angle. So this is the same as 5 cos of 0.219 plus j sine of 0.219, like that. Okay, so remember here your angle is in radians. So if you're going to calculate cos of this, make sure that your calculator is in radians. Otherwise, the value you get will not be correct. Okay, so substitute that work out cos of 0.219, and then you multiply it by 5. I'm getting 4.881, so to 3 decimal places. And then the same thing with this sign. I work out 5 sine of 0.219. Again, my calculator must be in radians, and I'm getting 1.086J. So this is in polar form, and that is in rectangular form. Somebody's mic is not muted. Some music in the background. Please mute your mic. Okay. Right. So that is how we would do it. Then writing complex numbers in polar form help us to work out the logarithms of negative numbers. Remember when we were doing logarithms, we said log of a negative number is undefined. So if I asked you something like this, what is log of -1? This we would say is undefined. Okay, and you cannot work this out, or it's not a real number actually. But now that we've written our complex numbers in exponential form, actually work out what log of negative numbers are. Okay, so if I gave you z, this is equal to theta j, and then I said, can you tell me what is ln of z? You know that this is ln of e to the power of theta j, and this would just be equal to theta j. Okay, but the thing about angles is that they, because they are revolving, angles may have different values, but their sine, cos, and tan are the same. But here you'll notice that I have just theta j, but theta and theta plus 2 pi, these two are at the same position. Okay, so when I take sine of theta and sine of this one, I'll put it in brackets. If I take sine of theta and sine of that one, their values are the same. Okay, but notice when I plug it in over here, the values will not be the same, because if I, let me just move up. Okay, if I have ln, and here I have 0, sorry, not 0, it's theta, theta plus 2 pi j. When I take ln of that, the answer this time is theta plus 2 pi j. These values, that one and that one, are not the same, even though our angles are actually equal. So when I ask you to work out ln of z, somebody might give me this one, and they are correct because that is the position of the angle, and then another person could give me that one, which is also an angle at the same position. Now, to avoid these many answers, we have what is called the principal value. Okay, so that means I want to work out only one specific value for ln of z. Now, to do that, we first have to understand what is our principal argument. Now, when I draw my plane over here, I can say, give me an angle. Let's say I have my complex number over there, and then this is theta over there. Okay, now theta, I've said there are several ways of writing it. You can, measuring it. You can measure it anti-clockwise, then it's positive, or you can measure it anti-clockwise, then it is negative. Okay, now the principal argument that is where we will get our principal value from. So you get the principal argument by taking ln of the principal value. Okay, so the principal argument is always between minus pi, write this, it is always between minus pi, then you have your theta there, and pi. Now what that means is if it lies here, so if you have the option of measuring it this way or that way, you can see that they are equal. In this case, you must take the positive one. So that means if you have the option of choosing either minus pi or pi, you must choose positive pi. Okay, so you do not choose negative pi over positive pi. Now with other angles, you have another angle. Let's say it is in the third quadrant. You have the option positive or negative. You must always look at which one of these is smaller and then take the smaller one. Now if my angle, we'll go quadrant by quadrant. If my angle is in the first quadrant, so I have that. If I measure it anti-clockwise, that is smaller than when I measure it anti-clockwise. So if my theta is in the first quadrant, I must take it the way it is. Okay, so that's first quadrant. Then if it is in the second quadrant, I draw the plane again. This is where your complex number would be. This is measuring it clockwise, that's positive. And then if I measure it anti-clockwise, I measure it like that. So again, you must always take the smaller one. So this one over here is going to be the principal argument. Okay, so the angle you take is going to be the positive one. So first quadrant, I pick the positive one. Second quadrant, I pick the positive one. What I am doing is always picking the smaller one. Then in the third quadrant, we draw a sketch. This is where my complex number would be. If I measure it anti-clockwise for the positive value, this is what I will get. And then when I measure it anti-clockwise, that is what you get. Now you can see for this time, the negative one is smaller, and I always want the smaller one. So this is going to be my principal argument. Okay, so in the third quadrant, if your angle is in the third quadrant, you take the negative one. Okay, then in the fourth quadrant, if I draw it, this is where my complex number will be. So I can measure it anti-clockwise. This is what I have. And then when I measure it clockwise, there it is. And then I'm always picking the smaller one. So this is my principal argument. Now, first, second quadrant, you pick the angle in the first and second quadrant. That is the positive one. Third and fourth quadrant, you pick the negative value. So you measure it clockwise. Okay, so you're always picking the smaller one. If it lies on the line here, then you must pick the positive one. Okay, so any other scenario, if it lies here, let me just use another color. If it lies here, that measuring it clockwise is still smaller than if you were to measure it anti-clockwise. Okay, so let's look at some examples of how we will find the principal argument. Oh, sorry, the principal value. So you have a question like this. It says find the principal value of ln of 3 pi over 3 j. Okay, so whenever we're given a complex number like this, first thing you need to decide is the angle there that we are given the principal argument or not? If it is, then just apply ln the same way we always do. Now here I have pi over 3. Pi over 3 is 60 degrees, so that is in the first quadrant. It is positive, so I take it the way it is. So to work out the principal value over here, I will just work out ln. The laws of logarithms still apply. If I have a product like I do over here, I split that and make it a sum. So this is just ln of 3 plus ln e pi over 3 times j. Okay, now this exponent over here, you know it comes down from your laws of logarithms. I have ln of 3 plus pi over 3j and then ln of e. But you know that ln of e is equal to 1. So I have ln of 3 plus pi over 3j. Okay, so given a complex number in exponential form and I ask you to find ln of that complex number, all you need to do is check, is the angle I am given there the principal one? If it is the principal one, go ahead and work it out. Take ln, it's fine. If it is not the principal argument, then what you need to do is first convert it. Okay, let's look at one such example. Okay, let's say I tell you to find the principal argument of E5 pi over 4j. Okay, ln of E the power of 5 pi over 4. Now 5 pi over 4, that is, what is that, 225? Okay, yes, it's 225. Now 225 degrees, if I were to draw it, that is where it is. So this angle is positive, so obviously I have measured it like that. But we say that in the third quadrant, what I need to use to get my principal value is this one over here. Okay, so if I have 5 pi over 4 here, to work out this one, I just say 2 pi minus, I'll say 2 pi minus 5 pi over 4. This is 3 pi over 4. Okay, so this angle here would be 3 pi over 4. But because I'm measuring it clockwise, then the angle becomes negative 3 pi over 4. Okay, so when I rewrite this over there, I rewrite it with the principal argument. So this is E minus 3 pi over 4 times j. Okay, and if you were to okay, that's better. And if you were to draw this or sketch it, you will see that minus 3 pi over 4 is at the same position as 5 pi over 4. So I've just rewritten it with its principal argument. Then I take ln the same way that I always do. So this will just be minus 3 pi over 4j. That's it. Okay, the value of r here is 1, but we know that ln of 1 is equal to 0. So I have 0 minus 3 pi over 4j, and that is why that is my answer. Okay, let's look at some more examples. Finding the principal argument. I have ln of 2, and here I have 30 degrees. Now, if your complex number is not given in exponential form, the first thing you have to do is convert it to exponential form. And very important, your exponential form must have theta in radians. If theta is not in radians, then what you have written is not defined. So first thing, make sure it is in exponential form, and then for exponential form, theta must be in radians. Sorry, I'm missing, this should be a minus. Okay, so to convert this, I will have ln, and this is 2. Then I will have e to the power of minus pi over 6j. Okay, so we know that minus 30 is the same as minus pi over 6. And then I just substitute them at their places in the exponential form. Right. Then I ask myself, is minus pi over 6 the principal argument? I can always sketch minus pi over 6. That means I must measure pi over 6 radians clockwise, and then I will end up in the fourth quadrant. So it is the principal argument, so I just evaluate it. So I have ln of 2 minus pi over 6 j. That is my answer. If I have ln of 1 minus j, here my angle is in rectangular form. First thing I need to do is convert it to to exponential form. Okay, so to convert it to exponential form, what I need is r, and I also need theta in radians. So r here, this is just the square root of 1 squared plus minus 1 squared, which is the square root of 2. Okay, and then here my complex number lies in the fourth quadrant. Okay, so what I can do is I know that this angle over here is equal to the reference angle over there. Okay, because I can see it's in the fourth quadrant, the principal argument must be measured clockwise. So the value is the same as the reference angle over there. The only difference is that it is negative. So my theta is just going to be negative tan inverse of 1 over 1. You can do the whole procedure of working out the angle in the fourth quadrant. So say 2 pi minus tan inverse of pi, and then work out this part over there. But I hope you can see that it is equal to that. And then this is just equal to minus pi over 4. Remember, I am working with radians only. If it is in degrees, then it is not defined. We don't want that. With exponential form, we are only working in radians. So I am taking, let me see my question. Okay, so I'm taking ln of the square root of 2, and then e to the power of minus pi over 4 times j. Then I will have ln of square root of 2 minus pi over 4 j, and I work it out. That is my principal value of ln of 1 minus j. Okay, so remember, there are several solutions, but we are looking for a specific one, and that is the principal argument. And now, what I said at the beginning, what is ln of minus 1? Okay, so previously we couldn't work this out, but we know minus 1 is a complex number, and we can rewrite it as such. If I were to draw the diagram, minus 1 is over there. So the angle over here, remember, if you look at these two, I have a choice between minus pi and pi because neither one is bigger than the other one. And I said when you have a choice between pi and minus pi, you must always pick the bigger angle as your principal argument. Yeah, the bigger one, the positive one. Yeah, but pi is bigger than minus pi. Okay, so then I know what r is going to be. R is just equal to 1, and I can show that. This is the square root of minus 1 squared plus 0, and then this is equal to 1. So I have my r and my theta. So ln of minus 1, this is just equal to ln, and then I have e to the power of pi, not minus, pi j. Okay, so that's what I have over there. Okay, so the coefficient is 1, but I don't really need to write it. And we know that ln of 1 is equal to 0. So this, okay, I'll just work it out. Plus ln that, which is just pi j. And this is 0 plus pi j, which is just pi j. Okay, so let me see if I have more exercises here. Okay, so that is all the questions I have. There are some more questions in your books that you can try. So all of these I got them from your book. So you can look at the ones that I didn't do and then do those ones as homework. Now there are some interesting questions about proving De Moivre's theorem using this complex numbers. So we'll start with the first one. If you remember the product of complex numbers using De Moivre's theorem, I have two complex numbers, z1 and z2. This was equal to r1, r2, and then I will add the arguments. This was the formula using De Moivre's theorem. Now in your book it says prove that this is true or confirm that this is true using the exponential form. So here I will just rewrite z1. z1 will be equal to r1 e to the power of theta 1 j, and then z2, this is r2 e to the power of theta 2 j. Now if I multiply them, I just need to remember my laws of exponents. So z1 times z2, this is the same as r1 e theta 1, I'm trying to write a small one there, and then j, this is r2 e theta 2 and j. Now multiplying this, I will get r1 r2, so I can just multiply these two numbers, and then here the bases are the same, so it's e, and then when I'm multiplying and the bases are the same, then I just add the exponents. So I have theta 1 j plus theta 2 j. Okay, now I can factorize j out or count how many j's do I have. I have theta 1 j's and theta 2 j's. How many altogether? It's just theta 1 plus theta 2 j's altogether. So this is r1 r2, and then I have e theta 1 plus theta 2 j. Now this r1 r2 is a number. Okay, so you can think of it as r, and then here theta 1 plus theta 2, those are in radians. So when I combine two radians, I will get another theta in radians. So this is still in exponential form. And from here, I can rewrite this in polar form. This is just my r, but here my r is the product of the r1 and r2. So I have r1, r2, and then my angle, it's just this one, theta 1 plus theta 2. And you can see this is exactly De Morgan's theorem. Okay, so the one for raising to an exponent, you have z to the power of n. Go ahead and try that one. So first I want you to rewrite it in exponential form like I did over here, then raise it to the power n, and then show that when you go back to polar form, you will have r to the power of n and then n times theta. Okay, you can also do the same thing with the division. You can see those questions. I don't have the numbers of the questions here with me, but you can see it asks you to show or confirm that De Morgan's theorems are actually true. Okay, so I think that is it for today. We've done a lot of exercises. The ones that I didn't do, again, please go and try them. If you have any problems, you can let me know. Do we have any questions before we stop? Any questions?
No, ma'am.
Okay.
No, ma'am.
Okay, then if you're fine, again, I was recording this. I'll just put it, I'll send you guys the link. Did you manage to get the other one? The link?
No, miss.
Or did I not
No,
send that one?
ma'am.
I didn't send it. Okay, it was done. I'll send it just now with this one. Okay, then have a good day. I'll see you guys tomorrow, 7:30.
Thanks, miss. You too.
Okay, bye.
Bye.